Let's plot points at -2, 4, 0, 0, and 2, 4, and connect them to form a standard parabola. When we translate a function like this, we aren't bending or stretching its core shape. We are simply taking a rigid structure and sliding it to a new location on the Cartesian plane. To control that movement across any family of functions, we use a single baseline formula. The q at the end of the equation acts as our vertical slider. Because it is added to the entire function, it directly impacts the y values. Add to q and the graph moves up. Subtract from it and the graph moves down. Inside the function, the p parameter acts as our horizontal slider. This is where the math can feel counterintuitive. To move a graph to the right, we have to delay the input. That means an operation of x minus p shifts the graph to the right, and x plus p shifts it to the left. Mastering these two sliders gives you absolute control over a function's position. You can predict where a graph will land without having to recalculate its core shape from scratch. Let's apply this to an equation. We have the function f of x equals 2x squared, alongside the instruction to translate it 3 units to the left and 1 unit down. To accurately shift the graph horizontally, the shift must sit inside the bracket, directly attached to the base x. So we replace x with x plus 3. Then we subtract 1 from the entire expression for the downward vertical shift. When we move to hyperbolas, the focus shifts to the asymptotes, the boundary lines that define the graph's position on the axes. Look at our new target equation on the right. We extract the parameters directly from the equation. The denominator is x minus 3, giving us a horizontal shift of 3 units to the right. The constant at the end is a positive 4, giving us a vertical shift of 4 units up. We move that structural frame first. The vertical asymptote shifts right to x equals 3, and the horizontal asymptote shifts up to y equals 4. Once the frame is set, the hyperbola curves snap neatly into their new positions. Translating the asymptotes first makes plotting the actual visible function mathematically foolproof. Let's test that bracketing rule. Take the linear function -2x plus 3. Write down the new equation if it is shifted 2 units to the right, and simplify it completely. Pause the video and try it yourself. Because we are shifting right, we replace the x with x minus 2 in parentheses. Distribute the -2 to get -2x plus 4, then add the 3. Your final simplified equation is -2x plus 7. These translation parameters allow us to determine vital properties, like a function's domain and range, purely through algebra. We can find the boundaries without ever needing a sketch. Here is an exponential function. By looking at the equation, we know its domain includes all real numbers. Its horizontal asymptote is y equals -2, which means its range is restricted to y values greater than -2. Now we apply a shift right by 1 and up by 4. Moving right doesn't restrict the domain of an exponential function, so that remains all real numbers. But the vertical shift moves our horizontal asymptote up by 4 units. -2 plus 4 is 2. Our new range is y greater than 2. Algebraic parameters are the DNA of the graph. Reading them directly identifies every geometric property without relying on a sketch. We can also perform this process in reverse, building an equation using the location of the asymptotes and a single coordinate. We start by locking in the asymptotes to find our p and q values. The vertical asymptote is at x equals -2, meaning p is positive 2. The horizontal asymptote is at y equals positive 1, so q is 1. We plug those into our hyperbola formula. To find our final missing variable a, we substitute the coordinates of our point, 1 and 2, into the equation. Subtract 1 from both sides, multiply by 3, and we find that a equals 3. This chart summarizes the mechanics. Vertical shifts use the q parameter and move the graph up and down. Horizontal shifts use p, moving left on a plus and right on a minus. Mastering these p and q sliders allow you to predict the movement of any function family, moving between the equation and the Cartesian plane with precision.
You've watched the lesson. Now take your learning further. Explore clear explanations, worked examples, and focused learning activities. Test your understanding with interactive questions and immediate feedback. Work through targeted questions and build the confidence to solve problems independently. Continue this topic on Relearn. Learn it, practice it, and master it.